I'm Cindy Kelly, Atomic Heritage Foundation. It is Wednesday, April 25th, 2018, and I'm in Oak Ridge, Tennessee. And I have with me Kevin Clarno. And the first thing I want is for him to say his name and spell it.
My name is Kevin Clarno, Kevinclarno.
Great. So what I would love to hear first is a little bit about yourself, about where you were born and your childhood and how you got interested in being a scientist.
I was born in Illinois and moved to Texas when I was 8 years old. And so growing up, my dad was a wastewater engineer and worked on a variety of projects from the dirty water to clean water, and has gotten involved in dams and dam safety in the Lower Colorado River Authority area of central Texas. So growing up, I've been involved and gotten to see all kinds of engineering things, and my dad had Popular Mechanics laying around all the time, and I loved picking up his Popular Mechanics and just reading all the different fascinating stories and engineering news records and what's going on. And so those things were just laying around the house, and so, you know, with free time, I would pick it up and start reading it and exploring what kinds of things are going on in the world. And just the whole concept of all of the different pieces that get built and created and the new technologies that are coming have always fascinated me. And so even at a young age, I excelled in math, but I really enjoyed science and building and construction kind of things. So as I was going through high school, we had a physics class my senior year and sat down and started looking at different energy choices and energy options and you know, the concept of climate change and is it real and where's it coming from? And as we were talking about and working through these issues, it just became clear that energy density is such a big, important factor in what we do. With coal and oil, you're breaking chemical bonds to release the energy. With nuclear, you're breaking the atomic bonds. And so you need hundreds to thousands times more mass to produce the same amount of energy. And so it takes hundreds of train cars of coal or oil to produce the same amount of energy in just a pencil eraser size piece of uranium fuel. And so it became very clear that they're just simply to produce this energy, we'd need fields and fields of solar panels or wind turbines to compete with the same amount of energy that's produced in just this tiny little piece of this uranium. And there's so many places throughout the world that have a lack of energy, and energy is going to be needed more and more as third world economies start growing and turning over. So there's going to be never going to be a lack of need for more energy. And so it became clear that we needed a very heavy energy density source of electricity. And so it was clear that in the long run, even as new technologies and energy efficiency improve, there was going to be a strong need for nuclear energy, for nuclear fission power. And so as a high school senior, early on in my senior year of high school, I realized this is something that just makes fundamental sense. There are all kinds of issues surrounding it, and the more I've been in the field, the more I've learned. There are all kinds of regulations and challenges, but deep down, the same fundamental principle holds. You have a huge amount of energy in a very small space, and all of the waste from that, it starts out in a metal tube and it just gets hot. And when you're done and you're ready to get rid of it, it's still contained in that same metal tube. You don't have to have filters. You don't have to have anything trying to catch and capture the waste coming from this. And so it just makes inherent sense. So it's been fascinating to have that as my career, to try to help it get implemented correctly in a way that's efficient and can last.
So currently, what's your angle on this, or you know, what are you doing to achieve your goal?
Well, so right now I'm the director of a consortium of a whole bunch of universities, national laboratories, and industry partners, where we're working together to identify what are the biggest challenges in the nuclear field that are addressing industry right now. And so the industry has identified there are several things that if we could overcome these could make nuclear power significantly cheaper and we could significantly understand the safety of these reactors, so that we can understand where we're wasting excessive throwing away fuel out of overly cautious margins. And so understanding where are there excessive margins that can be reduced that aren't providing value to the industry or adding to the safety of the plant. And so we are using the supercomputers here at Oak Ridge. So we're using some of the fastest computers in the world to create computer models of how are these reactors operating and what would happen if there were an accident, to understand exactly what's going to happen. Because we have almost 100 plants in the U.S. that are operating nuclear reactors, providing 20% of the electricity for the country. And with that, these reactors are operating, and they're operating safely, effectively, efficiently, and they know how to run these plants. But there is no reason to take any risks with regard to safety. And so what we're able to do is we're able to create computer models that predict what is happening in the plant today, and be able to say, well, what would happen if tomorrow something failed, some safety system failed? What would happen to the plant? What would happen inside of that reactor plant?
So this goes to anticipating emergencies and also in the design of the next generation?
Yes. So our current focus right now is understanding the biggest challenges in the existing plants. And so we've actually focused on light water reactors and almost entirely on just one piece of those, which is 70% of the light water reactors, the pressurized water reactors. And we're trying to understand their biggest issues and understand how we can use these advanced tools to overcome it. In an industry that is very conservative, they are not bold in taking new risks and new options. They don't want to make any change that would in any way put the plant or the investment, let alone the safety of the public, at risk. And so we have to do a lot of work in order to demonstrate we really do understand exactly what's happening inside of these systems. And inside of these systems, you have very high radiation environment, very high temperatures, coolant flowing. And so you don't wind up having a whole lot of sensors and detectors to know exactly what is happening in every single location. There's no eyes that you're putting inside of these reactors as they're operating. And so through our simulation tools, we're able to give a clear picture of this is what is happening at every single location, every single millimeter inside of the plant. We're able to give them a perspective of this is what it looks like and this is what is really happening, to a resolution they've never really had before. And so we're modeling all of the corrosion that's building up on the outside of these protective metal tubes to understand how much corrosion's building up, what's the effect of that corrosion. It's a protective layer, so for some elements it's good, but if it gets too thick, it can capture some of the other chemicals that are in the water that they use to control the chemistry, and it can become bad. And so understanding in very high detail what is happening, where is it happening, we can help the plants identify how can they operate the plants, how can they tweak the chemistry in the coolant, how can they adjust the way they're operating so that they're operating as safer, that they can increase the power they produce without impacting the safety of the plants or the public at all.
And the industry has asked for that. I mean, they're part of this consortium, so
yes.
they've identified here some of the questions we have.
Right. So this started in 2010. There was a call for proposals, and the consortium that we have wound up winning the proposal, and it included Westinghouse, which is one of the main fuel manufacturers in the U.S. and had designed many of the plants that are operating here. It also included the Electric Power Research Institute, which does research throughout the country on electric things, and one of their main elements, or electricity generation, and one of their main elements is nuclear power. And so they are a research service organization to the nuclear power industry throughout the country. And so they do a similar thing to what we're doing, but we are able to leverage all of the expertise at the national laboratories and universities to do it collectively. And then we also had as one of our prime partners the Tennessee Valley Authority, which operates a suite of nuclear reactors here in the South, including Watts Bar Unit 1, which has been operating since the 90s and is 30 miles down the road from Oak Ridge. And they recently turned on Watts Bar Unit 2. And so in 2010, this was that was the primary industry partners that we were working with. And so we were able to get all the information we needed on the plant design from Westinghouse, the fuel that's gone in for the past 20 years. We've been able to get a clear picture and understanding of how is a reactor being operated, and then develop the modeling and simulation tools to predict the full history of how that Watts Bar Unit 1 plant has operated. And through that, we've been able to look at some of the challenges they've had throughout the years. In the early 2000s, they had one of these chemistry problems. And so for a year and a half, they were operating, and they wound up having to reduce their power and shut down for a while to understand what's going on with this chemistry and how do we fix this chemistry problem. We've been able to go back and look at the history of it and model and show this is what was happening with that chemistry issue. This is where you were having this corrosion product build up on the surfaces. So now as we're able to show this is what happened then, as other plants are concerned about the risk of having to shut down or reduce their power, we're able to say, okay, let's set up and make a model of your plant and predict what the life of your plant from the past, but also going forward. And going forward in this next operating cycle, we're going to help you understand what is the corrosion that's building up on the surface of these rods, and how would that have an impact on your plant operation, so that they can make better informed decisions about how much new fuel do they need to add. Because the conservative thing is, let's just get lots of new fuel, because some of this fuel that's been in for a while, it still has plenty of uranium, it still has plenty of energy stored inside of it. It's conservative to say, well, let's just throw that aside and throw it away, but you're just wasting this resource. And so by being able to help them understand the operation of these plants, the chemistry buildup inside of these plants, they're able to identify which of these fuel assemblies can they keep and let them stay in longer to use more of that fuel up. It's corrosion on the outside of the fuel rods. So the fuel is on the inside, and the water flowing past it has this corrosion, this crud build up on the surface. And so once they understand that that's there, it's okay for it to be there. But if it builds up too thick or it captures too much of the boron that's in the coolant, then it can actually cause the neutrons to get absorbed in that instead of getting absorbed in the fuel, where it's going to cause more fission. And so it wastes those neutrons, and it drops the power in the top half of the reactor down to the bottom, and can impact the safety systems. And so when that happens, they have to reduce the power. And so by helping them understand how close are they to that, to a risk of that happening, they can decide, we want to purchase less fuel, keep some of this older fuel in for another round, and we save the cost of that fuel.
And you can pinpoint the corrosive elements.
Yes. So we're able to model. So what we're modeling is, we're modeling the neutrons hit a uranium, cause a fission, and send out more neutrons. And so we're modeling the distribution of those neutrons throughout the entire reactor plant. As it's producing those neutrons, it's heating up the fuel. And so the fuel is getting hotter, it's thermally expanding, it has all kinds of radiation effects on materials, so cracking and breaking of this fuel inside of this individual fuel pellet. But it's getting hotter, and so all that heat is going out of the fuel pellet through this metal tube cladding, and outside of that metal tube you have water flowing past to take the heat away. And so at that cladding and coolant interface is where you have this corrosion that will build up. And so we're able to model every single fuel rod, every single fuel pellet in the entire core, all with very high detail, all understanding through this radiation interaction what are the individual chemical elements that are here, what elements do they form, what's the mechanical structure and rigidity of the materials involved, and what is the corrosion buildup on the surface of these rods, so that the plant operators can understand how close are we to one of these power anomalies happening that will cause us to have to reduce power or shut down for a while.
Well, there's so many variables too. Who made the aluminum clad?
Yes.
Who made, and when was put in, and the corrosivity of the water that probably changes.
Right, and even the past operation, because many of these fuel assemblies will stay in for 2 or 3 cycles. They'll be in the plant for 4.5 years. And so you can't just model what's happening today. You have to understand everything that happened for the past 4.5 years. And even before that, because the fuel assembly that's in there now was impacted by what assembly was it sitting next to 3 years ago. And so you really have to understand the full dynamic of how the plant has evolved and operated through the years.
So the plant has to be very cooperative with you to give you all this information.
Yes, and that is what has been so unique and exciting. Earlier in my career, I was working doing somewhat similar simulations for the Nuclear Regulatory Commission. And the regulator does not necessarily get every ounce of data that exists, every specific enrichment of every fuel pellet. But this is something that the manufacturers of the fuel have. This is something that the operators of the plant have. So by being in partnership with them, they have been able to supply us with, here is the data, this is what's happening. And so in the beginning, they were saying, okay, here's the average of these hundreds of pins power distribution. And they were giving us this very coarse data, and we started to show them we are giving predictions on a centimeter basis. And they said, oh, well, we have better data than we gave you. We just didn't think you'd know what to do with it if we gave it to you. So they've started to give us more and better data. And even now, as we've started generating these models and comparing them to the measurements that they have in plant, while limited in measurements, they have some. And some of the differences that we're seeing, they're starting to wonder, is this because of the specific manufacturer unique things of each individual fuel rod? And so one of the things that we're going to probably start looking at in the near future is what is the enrichment of every single fuel assembly? How much uranium-235 is in every single fuel pellet as it goes up axially in each one of these 50,000 rods in the entire plant? They have other things that they put in the plant to help control how it operates and keep the power distribution flat and effective and efficient. And so understanding all of these others, where are the uncertainties, where are the unknowns, and how do these unknowns impact these predictions that we have? And it's years of operation at these plants where they didn't necessarily see the potential long-term uses of this data. So even in the collaboration with the plants, some of their early data they have stored in paper files. They have stored in boxes somewhere off in the corner. And so the newest data, it's relatively easy for them to say, okay, let's just get a data save, and we save it to this computer file, and we make this file available to you. But we want to be able to go back to the very beginning. What happened in the beginning? What accidents, what issues, what challenges did you have between day one you started the plant and today? And so to get those records, they have to go back into their files and dig through the paperwork to try to figure out what were the measurements back then, what was the loading and the enrichment.
You think you want to do a statistically representative sample. I'm sure that's a lot of work.
It is, but it can provide tremendous value. Because in the end, we have to make the case that our simulation tools are modeling their plants correctly, or they should not trust that what we tell them is valid.
Right.
And so the more data that we can have to show, I didn't just guess and get a snapshot right today. I've been able to tell you what was happening in your plant, show you what was happening in your plant, and help you to understand why it happened. Because there were many issues that they had 20, 15 years ago that they know what happened. They have a pretty good idea of why it happened, but they have only coarse picture of where it happened and how it happened and what they could have done differently to prevent it. And so now we're able to go back and show them in this great detail, this is exactly what happened and where it happened and why, so that they can start asking the question, well, what do we do so that it doesn't happen again?
Well, that's interesting. I certainly hope that you're going to be able to extrapolate from this one plant. Maybe you have to do 2 or 3 of these before you see the patterns. And come up with some general prescriptions. Yes.
Well, it's changing in many ways the way that the DOE research labs can now interact with these commercial entities. As TVA was starting their Watts Bar Unit 2, which just started in April 2015, we started predicting what would happen before they started up. And so before they even turned anything on, we started telling them, this is what you're going to see. Now, obviously, to get the plant turned on, the people that sell them the fuel, the people that design the plant, have to tell them that also. But they were able to take those predictions that were at the more coarse scale and ours with tremendously high resolution and be able to overlay them and understand, are there differences? Why are there differences? And then when the plant started, be able to evaluate which one was more correct. And we continued to work with them. And so instead of getting in the traditional plants going back in those records, we might get here's a data dump once a month. Well, with Watts Bar 2, TVA was supplying us with these data dumps every hour. And so every single hour of operation from April 2015 to December, when they went to full power commercial operation, they were giving us hourly snapshots of exactly what was happening. And so we were able to take the tools and look at every single test, every single ramp up and explore, is this system working what we expect? Okay, let's shut down, let's retest again, restart. And so through that entire period of time, we were able to do these hourly evaluations of the accuracy of our software compared to what is happening. And through that process, they went through so many power up and power downs, we have been able to show and build a lot of confidence that we know what's happening inside of that plant today better than any measurement tool they have, because the measurement tool is taking it at one particular location and we can tell them the picture everywhere.
Oh, that's very interesting. I'm just thinking now, the B reactor, if you've been there at Hanford,
Mm-hmm.
they had gauges for every single one of the, certainly of the fuel, the containers,
Mm-hmm.
the rods that contain the fuel rods, the larger element. It's not each little,
Right.
Yeah.
And that's critical on small test reactors where you're trying to understand how this reactor is operating. It's critical to have all of these measurement devices. And so the test reactors that have been produced, that were developed throughout the world, were generally extremely well instrumented, identifying flow patterns and temperatures and radiation flux measurements. And it's extremely useful. But that is when you're trying to understand how this system works. Well, the commercial plants, they don't want any of those things in there because they're a cost and they're a hazard. If you have an extra flow meter sitting inside of it and it actually breaks off and goes flying around the reactor, it can cause damage. And so they want to have the minimum amount of, they want to have a sufficient number of detector and measurement devices, but they don't want to have an excessively large amount because it's not adding any value and it can create risk. And so, yes, it would be handy as a computer simulation person to have the data of every single ounce of information there, but it's not a reality in these operating plants.
So, of the 100 plants that are in operation now, what percent are light water?
In the U.S.,
Yeah.
all of the commercial plants
All
are
of them.
light water reactor. Yeah.
So what you're doing on light water
Yes.
is potentially going to help those 100 plants.
All 100 of those plants.
Yeah.
Absolutely. That is the goal. And we are working, the original team had Westinghouse and TVA and EPRI, but as we've continued to develop these tools, we have a guiding industry council that is composed of other fuel vendors and other utilities. And they're giving us input on what is important, what do we need to be doing, how should we change and restructure things so that the work that we're doing can impact the nuclear industry broadly. And so, and this, because it's been happening over the past 8 years, this has incorporated changes in the energy picture in the U.S. There's a whole lot more wind and solar online today than there was when the original proposal was written. And so today, energy markets are different. There's a lot more variability because sometimes the wind's blowing and sometimes it's not. And so the energy prices, electricity prices, will go up and down throughout the day. And so the entire climate of how these nuclear utilities are operating these plants has changed and become more challenging because in the past it has been, there's always a certain amount of, 80% of the maximum energy used during the day was used at the lowest time. And so there was this base load amount of electricity that you always needed that. Everyone throughout the day, even at the lowest electricity time, you were going to have this amount that was used. And so there was a place for nuclear power, which is very expensive to build, but inexpensive to operate at just a constant power. And so there was this perfect place where nuclear energy filled a void to be able to supply that base load power. And then you'd have other sources that were easy to just turn on and turn off, like natural gas, that would supply the other 20 to 30%. And so that base load piece, coal and nuclear, really filled that margin. And so as there was talk of coal going away and reducing greenhouse gases, it made perfect sense that nuclear would fill that piece of the void. But because of the introduction of so much more solar and wind, there are times when that is supplying 80 to 90% of the electricity.
Solar and wind.
Solar and wind in certain markets. So Illinois, for instance, there have been a lot of tax credits and subsidies to help encourage these wind power wind farms. And so because of that, the electricity prices can vary, and in fact, it can be negative. So in the federal government provides a tax subsidy for how much energy is produced. And so they'll say, independent of the cost of electricity, we're going to give you this much in tax credits. Well, the utility, if there's an excess amount of electricity available, the wind power companies can say to the state, I will actually pay you to take my electricity because I know the federal government is going to pay me more. And so it produces negative electricity prices where the utilities are paying the state, will you please take my electricity? This doesn't make any sense, but it's what can happen when policies go wrong. And so in the state of Texas, growing up, my dad always talked about how there were wind turbines that were being built way out in West Texas, but all the electricity was being used on the sort of I-35 corridor and Dallas, Austin, San Antonio area. So lots of electricity used there. Not much electricity needed out in West Texas, but there was a requirement that 10% of new electricity generation be renewable. So the companies were building gas plants near the I-35 corridor where the people are, and they were building wind turbines way out in West Texas where the wind was blowing hard, but there wasn't enough capacity to actually bring the electricity to where the people were. And so out in West Texas, there was a lot of electricity being produced, but it wasn't even making it to the markets where it was needed until there has been more and more buildup, and they've started building in these big power lines to bring it there. And so Texas is another place where they have very variable electricity prices. They can cause challenge for some of these baseload power. And so the result is it's much easier to build natural gas, which today happens to be inexpensive. But electricity generation in the U.S. is a very long-term planning thing. Whether you're building dams or nuclear power plants, you're talking about billion-dollar investments and that have a return over 15, 20 years. And so it's going to take a long time to get that return back. And the uncertainty that exists because these electricity prices are so varying so much throughout the day, let alone year to year, just causes a lot of uncertainty that make utilities uncomfortable with building new expensive generating capacity. So it's much easier to say, well, gas is inexpensive now, so let's go ahead and build it now.
What about, one of the things they talk about with solar is, well, you need to store, if it's sunny for all summer and you get excess energy, but it's cloudy and rainy in the fall, that if you have battery storage capacity, then you can regulate these fluctuations.
Mm-hmm.
But for a base load like nuclear, and the market's not right, can you store it and then release it, in times when the prices are right?
Yes. So, that conceptually, absolutely. And there have been a variety of people looking at storage technology has been changing dramatically. You think of how big your phone used to be and how little battery life you got out of it 15 years ago, and now it has so much more power and so much more capability, and it weighs less and is thinner. So battery technology has just been advancing rapidly. And whether it's batteries or other things, the concept is the same of we need to be able to store this energy and use it when we want to use it. That could have a huge impact across the electricity markets. But it's unclear necessarily how that's going to happen or when it's going to happen or whether it's going to be one technology that revolutionizes things or even if it's the electric vehicle fleet, because if it's electric vehicles throughout the country, they all act as a energy storage because they can charge when it's inexpensive and use it whenever they want. But it also is going to have to change how pricing in markets work, because to the end customer, to the homeowner, there is little reason to charge your car at night as opposed to the day or at one time or another. And so a lot of things will have to change. And it's a struggle because very minor tweaks in energy policy can have huge impact to the electricity generating companies. Just this minor change in how much the tax credit you'd offer to the renewable generators can have a big effect on do electricity prices go negative or not, or how negative do they go. And so little small adjustments to policy can have huge impact downstream.
I can see it's really very complex.
It is. Understanding the technology is also hard because there are a lot of people with conflicting assumptions and interests. And so it's important that we have a strong technical foundation for the decisions that we make. We cannot gloss over the impact of understanding the science and the technology behind the things that we use. So many people just walk to their wall and they plug in their phone and they ask for it to charge, and this magical electricity takes care of it. But there's so much that goes on behind the scenes to provide that electricity to your house. And little things that many people can do throughout the country, whether it's individual homeowners or whether it's politicians and businessmen, small changes can make a really big difference in the technology developed and how things are used in this country.
Wow, that's true. I thought when you were beginning your last paragraph, you were going to talk about the importance of public understanding of how nuclear works, because there are certainly some myths and.
Absolutely. I think it's public understanding of technology in general. We need to have better public understanding of nuclear. There are a whole lot of misconceptions about the dangers of radiation, despite the fact that you get radiation from the sun every single day. But it's also understanding things like climate change, understanding policy impacts, and things that happen on page 3 of the newspaper can really have a big impact. It may not seem like much, but there are so many things that are happening throughout this world. And having a cursory look at whatever one thing concerns us today, and losing sight of the bigger picture and how all of the different things interplay is really lacking. And so understanding in depth the science and how the science works is critical. Because if you don't understand how the science works, then you can make foolish decisions or believe something somebody tells you even when it's not true. But we also have to understand how that science interplays with all of the other domains out there. My brother is a sociologist, and so he studies how people think and communities think collectively. And we, as humans, think collectively in many ways, and we need to be able to understand the technology, but also understand how we impact each other and the decisions we make impact the people around us. And so much of social media feeds are dominated by drama headlines. And so no one clicks a news article that said, today the nuclear reactor 50 miles away operated correctly and safely. It's just not a news story anyone cares about. But on the other hand, if someone were to say, I drove past a nuclear plant and I saw all kinds of white steam coming out the top of it, they'd put a news report out, despite the fact that it did that every single day. And thousands of people would see the article that said there was white steam coming out of the nuclear power plant. And so we have to have that fundamental understanding of the science and the technology in the world around us. But how you help people get excited and interesting about things worked as expected and designed is just not going to happen. And so how we go about that public communication, how we get the concept of nuclear as operated safely for generations, it's not clear how we can make that social impact. But that is a big challenge for the industry. So the question, what is the actual impact? How much money have we saved? So this program is 8 years into a 10-year program. It's been funded at $25 million a year. And every single one of these, every year and a half, a nuclear utility will do a reload, and they will take about a third of the fuel out of the reactor and put a third new in. And it costs millions of dollars for that new fuel. And these reactors are operating, and every day that they're operating, they are bringing in a revenue of about $1 million a day. But since they've been around for so long, and the fuel costs in general are low compared to their revenue generation, they're making solid chunks of money to be able to pay down their capital and generally operate in low cost. But the areas that we are really trying to impact the industry financially, this corrosion challenge, they recognize they could save about $1 million every single one of these reactor plants. Every year and a half, they could save $1 million. So there's a solid chunk right there. If we can build in that confidence that they start making decisions with our tools instead of the existing tools they have. we're doing a lot of work on understanding the radiation that is getting out into key structural components of the reactor. So the reactor core is sitting inside of one big solid chunk of steel, the reactor vessel that holds that water in there pressurized. And the life of the plant is really going to be dominated by the life of that vessel. And so if we can understand how much radiation is getting there, how much damage is getting to that plant, we can start to tell them, should this plant operate for 40 years or 60 or 80 or 100, 120? And so if we understand this key critical component that when it goes bad, it's time to just turn the plant off. If we understand when it's going to go bad, then we can help them know how long can they keep operating. Because that revenue, every single year they continue operating with the low fuel costs they have, they're able to just continue to supply very, very inexpensive electricity to the public. And then the other piece is understanding the safety. If they make changes in these plants, understanding what is the impact of changing out new safety systems. One of the trends in the industry right now is they're looking at more accident-tolerant fuel. And so can they design fuel that if there were an accident, if there were something that happened in the plant, this fuel would not have any problems. It wouldn't cause there wouldn't be any breaking of the fuel or any release of the fuel into the coolant. Now, there's several layers from the fuel being in the coolant to all the way out to the public to protect it. But if you have a massive release of fuel into the reactor plant system, you'll actually ruin that plant. And that's what happened with 3 Mile Island back in 1979. The safety systems were all worked as expected. The public was protected because of the big containment, but the investment of that electricity generation and the billions spent to create it are still sitting in the same state they were, sealed up, closed up, and not used again. And so being able to build in even more accident-resistant fuel inside of the plants, if we can get that fuel to operate just as cost-effectively as the fuel they're using today, but if there were an accident, they would still have the plant operating. They'd be able to turn it back on again immediately afterwards. Would be a huge increase in the financial investment in the safety of the system. And so we're helping to get a better understanding of how these new fuel concepts would get incorporated into the system. And then the other piece that we're doing is we're actually working with the regulator. So in this environment, these utilities, anytime they want to make a change, they have to explain to an independent Nuclear Regulatory Commission body what change they're going to make and how it is going to impact the safety of their systems. And so we're working with the regulator to help the regulator understand how this advanced computing and the software we're developing can help them understand the impact. And so in many cases, the industry may have a good idea, but they look at, well, convincing the regulator that it's a good idea is going to take forever, so let's forget it. And so by working with the regulator, we're hoping that we can accelerate the understanding and the evaluation of some of these new concepts so we can get these accident-resistant fuels on the market sooner and be able to transform innovations that you see in universities and laboratories on new fuels and new protective claddings, transform these innovations from the experimental scale all the way into production operating reactors, be able to make that process happen much faster with much better understanding of what to expect when you actually put it in the reactor.